Hello! In this video we are looking at continuous probability. So we're going to relate continuous probability to probability. Alright, we're struggling here. Probability. Relate continuous probability to discrete. And this is for learning intention 50. And I have this function sitting here, and this function is going to be my example for everything we're going to do in this video. So continuous probability, what's going on here? Well, if you remember, we did discrete random variables, and we said that you could get an x and it would be its value would be random. So let's just paint a picture of where we've come from. So let's start with variables. So at the very start of our maths, we said, all right, there are variables, and we solved an equation like 2x equals 4, and we said x equals 2. And we're like, great, x equals 2. That's a variable. We've solved for x. It's an unknown. Then this weird thing happened where we got random variables. We got discrete random variables. And we said, well, okay, we have this x, this capital X, but you don't really solve an equation. You have to do some kind of experiment to get the value. So you do an experiment and out pops some value for X. You might get 6, who knows, but it's a discrete random variable, and the value that pops out is discrete, so it's not going to be, it's going to be like rolling a dice or rolling die or flipping a coin or something like that. We've done discrete random variables where the output is based on some experiment. And then we got these tables where we said we had x and a probability that x takes on a value of x. And then we said, okay, x could be 1, 2, 7, 9, but these probabilities had to add to 1. So in this experiment, the probability that x pops out to be 9 is a quarter. And this is the sort of thing we looked at. So rather than this equation stuff, we said, well, we don't know what x is, but we know when we run the experiment, there's a 1 in 4 chance out pops a 9. Now we're taking it to the next step. We're going to look at continuous random variables. And just before we do, remember we said that these probabilities have to add to 1. So these probabilities here, when you add them, add these, that equals 1, and we said that they all have to be positive. That's going to tie into continuous random variables. So I'm going to give a quick explanation of this. Don't worry if you don't get it all straight away, because we're going to use an example to look at this. Continuous random variables, they take their values from a graph. So let's say you have some curve that looks like this. There's your curve. Okay. And I don't know, it might go from -3 to 2. And we might have a continuous random variable x. And we want to know what this can come out to be. But here's the thing with continuous random variables, we can only tell you across an interval. So for example, the probability, so let's say this just ends at -3 and this just ends at 2. The probability that x is between negative 3 and 2. It doesn't matter if you use the includes here. That's where it gets really weird. But the probability it's been between negative 3 and 2, it's actually the area under the curve. Now, for this curve here, the area under the curve has to be 1. Just like these probabilities have to add to 1, the area under this curve has to be 1. And this is what we call a probability density function. This is called a probability density function, or PDF for short. So the probability it's between negative 3 and 2 has to be 1. However, if we wanted the probability that it's between negative 3 and say 0, what you would have to do is integrate from negative 3 to 0. And that area under the curve tells you the probability. So, I don't know, that's approximately, to me, might be like 0.45. So we can find the probability that x happens over an interval. So it's none of this business where x pops out to be a 9. It's even more vague. It's saying that I can tell you that the likelihood that x is going to be between negative 3 and 2 is 1. And I can tell you that the likelihood that x is between negative 3 and 0 is 0.45. But I can't tell you, it's weird because the more precise I get about x, the less likely that is to happen. So if I wanted to know the probability that x is between 0.000001 and 0.000000, what have we got? 6 zeros, 1, 2, 3, 4, 5, 6, 2. That probability is going to be really small because that's such a tiny interval. Yeah, that's such a slim slice of the area under the curve. It's going to be a really small number. It's very unlikely that it's going to lie between that interval. So that's the thing about continuous random variables. It has to lie within an interval. So that was a very hand-wavy explanation. We'll get into using this example to explore these more clearly. But remember this. This thing here, the probability density function, gives you the probability up here when you integrate. You have to integrate to get these probabilities. You have to integrate over an interval. You can't sub in a value. You can't. Integration is what you need to do. This is all about the probability density function. It's just a curve that's being used. It's very secondary to the whole operation. It's just sitting in the background. You need to integrate, and that will tell you your answers. All right, if that seems really vague, that's okay, because we're going to go through all the maths of this with this example. So this is all the maths you'll need to know. So let's consider this PDF. So we're gonna first, let's check if it's indeed a probability density function. So let's sketch it first. So we have f of x equals 3x squared on 2 for x is between negative 1 and 1, and it equals 0 elsewhere. So I'm going to sketch my curve first. Let's sketch it. Okay. Sketch the curve. Ruling up my axes. What does this look like? Okay, well, DRT, 4 labels, use your CAS, whatever. It's going to look something like this. It's going to be a parabola that has endpoints here and here. And if we sub in -1, we get 3 on 2. So this point is -1, 3 on 2. This point is 1, 3 on 2. And you can see that it's 0 elsewhere. So here, elsewhere just means everywhere else. From here to here, it's 0. Okay, so there's a sketch of our probability density function. Here's what we're going to check first. This is the first thing we're going to check. Is this a PDF? I've just assumed it is. Is it a PDF? It has to satisfy two conditions. The first is the probabilities that it spits out they all have to be positive. So you can see there's no negative area under the curve. Everything's positive. So that's the first condition that it needs to satisfy. So all the area under the curve happens in the top half of our Cartesian plane here. So that's the first condition satisfied. All the probabilities are positive. So all probabilities are positive. So we're going to give that a tick. So is this a PDF? Yes, because all probabilities are positive. Another thing, the area under the curve must equal 1. So this area here, the area under the curve, has to equal 1. Let's check this. So we've checked condition 1. Let's integrate from -1 to 1, 3x squared on 2 dx. Let's see, we add 1 to the power and divide by the new power. We get x cubed on 2 from 1 to -1 equals a half minus a half, which equals a half plus a half, which equals 1. All probabilities are positive. Area under curve is 1. So we've satisfied both conditions. This is indeed a probability density function. So yes, it is. That's the first thing you have to do. If you get something like this and they ask you, is this a probability density function? You have to check that it's all positive and that the area under the curve is 1. That's how you know. So if there was any area under the curve here, it wouldn't be. And if the area under the curve wasn't 1, it wouldn't be. It has to satisfy both conditions. All right, this wouldn't be any good unless we could find probabilities from it. So let's calculate a probability. So let's find a probability. So finding probability. Let's find the probability that x is between -1 and -1/2. So in other words, we're finding the probability that it's between -1 here and -1/2 about there. So we're finding the probability it falls within that interval, and we integrate across that interval. That's how we find the answer. We integrate from -1 to -1/2 across that interval, 3x squared on 2 dx, which equals, as we worked out before, x cubed on 2 from -1/2 to -1, which equals -1/2 cubed on 2 minus -1 cubed on 2. Let's go up here. So that's -1/8 on 2 minus -1 on 2, which is -1 on 16 plus 8 on 16, which is 7 on 16. There's our probability. So the probability that x, this continuous random variable, falls between -1 and -1/2 is 7 on 16. That's our answer there. So the probability it falls within that interval, which makes sense because it's slightly less than half. Slightly less than half there. So that's how you find a probability. Let's do another one for finding probability. Let's find the probability that it falls between 0 and 1. That our continuous random variable falls within that interval. So that's going to be this area here. Can you guess the answer already before we do it? It's going to have to be a half, because that's half the area under the curve. So let's check that. So we're going from 0 to 1, 3x squared on 2 dx, which is x cubed on 2, which is 1 cubed on 2, which is a half. There we are. So that's how we find probability. So we've looked at, is this a probability density function? Yes. And we know how to find probabilities. The next thing we should be thinking about is, how can we, given our probability density function, how do we find the mean? What do we expect from this on average? What do we expect the continuous random variable to be? What's the expectation? Well, here comes the formula for expectation. The expectation of our continuous random variable is the integral, and I'm going to put some limits on this integral. You just have to integrate all the way across the curve. Like, you just have to integrate all the area. So don't worry too much about those. X times f of x dx. That's how you find the mean for a continuous random variable. Very important formula. So that's the expectation for a continuous random variable. Mean for continuous random variable. Okay, so let's calculate the mean here. What's the mean outcome? Well, we integrate from -1 to 1 all the way across here. X times 3x squared on 2 dx. Then we've just got to do the integral. So that becomes the integral from -1 to 1, 3x cubed on 2 dx. And we add 1 to the power, divide by the new power, from 1 to -1, which equals 3 times 1 to the power of 4 on 8, minus 3 times -1 to the power of 4 on 8. What do we get? We get 3/8 minus 3/8 equals 0. Look at that. That's the mean. That's what you expect from this, which makes sense because it's kind of like the center value there. So on average, this continuous random variable is going to spit out the value 0. Alright, well, what do you reckon the median's going to be then? If it's symmetrical, what do you reckon the median's going to be? I reckon it's going to be 0 as well. But we better get the formula for that, and we better look at how to calculate the median. So I hope you've got the mean written down. Let's look at how to get the median. This is the formula to calculate the median. So it's the integral of from a to m. M is the median. This is what we want to solve for. F of x dx equals a half. So in other words, what we're saying is, how much area do we need under the curve? What interval do we need to integrate across to get a half? So we start from the far left and we keep integrating, and we say, how do we get to a half? Well, let's look at this. So a is just your left interval of -1. M's the median we want to solve for. F of x is our function, and that equals a half. Now we need to solve for m. So we're going to add 1 to the power, divide by the new power, and we're going to do our substitution. So we get m cubed on 2 minus a half equals a half. So we get m cubed on 2 plus a half equals a half. M cubed on 2 equals 0, and that means m cubed equals 0, and of course our median is 0. That's how you solve for m there. So with a trickier example, it might come out as something else. But most importantly, this is the formula we need to know for calculating the median. This is the median for a continuous random variable. Alright, what about the mode? We need to know the mode. So how do we find this mode? Well, the mode here, what we're looking for the mode is just, it's the maximum. So the mode, if you look here, continuous random variable. So the mode's a bit different. I've got my computer version of the textbook here. So they go blah, blah, blah about weight. Here we are, measures of central tendency and spread. So I encourage you to have a look at this as well. The mode is just the max value. It's just the maximum value. So you should really sketch the graph. So you can see there, it's just wherever you have your maximum value. So it depends, like if you've got a curve where the height is in the center, that's going to be your mode there. But if you've got these weird peaks, you have to look for the endpoints. So let's have a look here. Let's have a look back at our example. So the mode is just whatever value that gives us our max point. So we'd say this is bimodal, so it has two modes. So we say it's bimodal, and the modes are -1 and 1. So these are our modes, they're just the max points, which it doesn't really fit in with the mean and median, because it's kind of a weird curve. But if it was a more normal curve, like if it was more something like this, makes sense that that would be the mode. Like it's a more meaningful value there. But anyway, that's how you work out the mode. It's just the max value, maximum on PDF. Just the max. That's how you work out the mode. Alright, so we've done mean, median, and mode. The next thing to do is variance. Now this is quite a big formula, but it's just very much the same as our formula for discrete random variables. So this is the formula to get variance. So we integrate over the interval, the curve, x, f of x, dx all squared. Okay, this is variance. You might be thinking, what on earth is that? Well, it's very similar to the variance for a discrete random variable. If you remember, for a discrete random variable, we did this. Can you see how that's the same thing? You've got the x squared on the inside, you've got it all squared on the outside. So you can see how it's analogous to discrete random variables. But anyway, let's find the variance here. You notice here, that formula, that's the mean. And we've just got to square it. So in our case, the variance is going to be integrating over that interval, x squared times 3x squared on 2 dx minus the mean squared. The mean was, we worked it out before, was 0. So it's minus 0 squared, which is just 0, which is good. So this becomes, I won't jump ahead, this becomes the integral of 3x to the power of 4 on 2 dx. Here, now we add 1 to the power, divide by the new power, and go from -1 to 1. So that's 3, 1 to the power of 5, minus 3, negative 1 to the power of 5 on 10, which equals 3 tenths minus, and that's going to be a negative as well, so that's going to be plus overall. So it's going to be 3 tenths plus 3 tenths, which is 3/5. There's our variance, 3/5. So we need to know that formula as well. That's how we calculate variance. These are on your formula sheet for your exam. Finally, how do we get standard deviation? Sigma. Well, that's the square root of our variance, as we know. So we square root 3/5, and there's our sigma. All right, lots to take in there. Lots of formulas to know, lots of new concepts to understand. Read the textbook as well. Have a skim, see if that helps you. And if you have been, thanks for watching.